right, here we go. Today we're going to talk about the wave equation using PDEs. My name is NOORALDEEN Hani Abdulaziz Abdulmaqsood Aldeeb, matric number 209586.
Okay, my name is HILAM metric number 211373.
My name is REESHI Santakumar. My matric number is 210913.
The main topics of today, introduction, history, principles and applications, examples and conclusion. All right, we're going to start off by a quote by Anders A. Robinson. The wave equation behaves nicely in one dimension and in three dimensions, but not in two dimensions. In one dimension, waves on a uniform string propagate without distortion. Distortion here means without twisting or deforming. In three-dimension, waves in a homogeneous isotropic medium propagate in an undistorted way except for a spherical correction factor. Isotropic medium is a medium that has a physical property which has the same value when measured in different directions. As a result, by its very nature, 2D processing never can account for events originating outside of the plane. As a result, 2D processing is broken up into a large number of approximate partial steps in a sequence of operations. These steps are ingenious, but they can never give a true image. Next slide. So we start. The wave equation is a linear second-order partial differential equation which describes the propagation of oscillations at a fixed speed in some quantity y, where v is the velocity of the wave, as you guys can see in the equation below. The equation is a good description for a wider range of phenomena because it's typically used to model small oscillations about an equilibrium, for which systems can often be well approximated by Hooke's law. Solutions to the wave equation are, of course, important in fluid dynamics, but also play an important role in electromagnetism, optics, gravitational physics, and heat transfer. Especially important are the solutions to the Fourier transform of the wave equation, which define Fourier series, spherical harmonics, and their generalizations. Next slide. All right. Partial differential equations. When handling PDEs, we use the most basic theories primarily in physics and engineering to construct mathematical models. The most two common ones are Hooke's law, which is the force needed to extend or compress a spring by some distance, scales linearly with respect to the distance. And we also have Newton's third law, which, as we all know, is if an object A exerts a force on object B, then object B has to exert the same force with the same magnitude, however, with an opposite direction. A PDE has arbitrary functions in its solution. Arbitrary here just means random. In some cases, they can be functions of one variable that to come together to produce a multivariable function, u of x of y, of two variables, which is only partly arbitrary. The wave equation, we describe this equation as having only one space dimension because there is no other independent variable but time. It can be described in a range of characteristics such as its wavelength, period, amplitude, and wave speed of the wave. So we know that the wave equations need to be solved in space dimensions when it comes to a phenomena involving the propagation of singletons, and waves can exist in 2 or 3 dimensions. Portraying the movement of particles in the medium as wave functions will help us calculate the position, velocity, and acceleration of the particles at any time. Next slide. The history of the wave equation. All right, we're going to start off with in 1691, Bernoulli and solving the problem of the catenary, which was proposed to him by his brother. Bernoulli actually analyzed under the action of forces the shape that an elastic line can be assumed by studying the mechanics of elastic bodies, where the frequencies and the bumps in vibration of the strings were defined, and proved that strings movements consist of an infinite number of imaginary harmonized vibrations. In 1713, Taylor investigated the vibrating string. He gave it geometric arguments instead of using derivative. Therefore, he didn't actually write down the PDE. He just treated it as a series of individually vibrating points. In 1746, D'Alembert was the first person to discover the one-dimensional wave equation. And then 10 years later, Euler discovered the three-dimensional wave equation. In 1749, Euler also examined free vibrations of an elastic string without mass. D'Alembert developed his integration method for a system of linear equations. Therefore, the famous theorem that the solution for the free vibration of strings can be described by a trigonometrical series was established. In the 1700s, Bernoulli showed that an infinite summation of signs can represent the general solution of the wave equation with given initial conditions. And in 1750s, Lagrange used a mass model consisting of n masses interconnected with strings of no weight to analyze string vibration. So for Lagrange to obtain the same functional solutions as Euler, he solved the system of n+1 differential equations where n tends to infinity. And in 1800s, Fourier proposed that any function could be written as an infinite sum of trigonometric functions sine and cosine only for those whose period are integral divisors of the time of the original function. So just because the many engineering mathematics of motion and transformation has been developed due to that connection between the Fourier transform and the wave equation.
Thank you, ALDEEB. Now I'm going to explain about the motion of the wave in a string. The long wave propagation is a physical challenge that can be used to focus on many important elements that for propagation. In addition to the complexity of the long path, allows to use analyze the D'Alembert options for 1747 solution to the traditional difficulty of the propagation wave. And string instruments, including violin, harp, guitar, including the package of the studying the vibration of the vocal cords and string in and their mathematical and ancient meanings. And there are several techniques packages for the mathematical modeling of elongated yarns, including the study of the power, line mechanics, and road mechanics in textile and textile production. To analyze the anxiety, it's important to create an equation that describes the movement along the long road. When you are afraid to choose a path again, to consider the details of elongated path. Suppose that extended path during the travel period moves to a completely new element during the travel period and the travel function, so obtained by the interval of the period dx as shown in figure. To consider a stretching to the level efficiency to ignore the effect of gravity, and elongated rate to consider is elastic and untied. So this figure shows the deformed configuration of stretching. So the bending resistance, it is assumed that voltage of the wire remain constant while the wave is acting. So where P is the density of the mass and it's across the section of the thread is the mass per unit length of the thread. So elongated path is initially along the x-axis but moves along the waves as shown in figure. So consider the equation of the motions of element. So we have this equation. We drive everything, including differentiation and equations. Then finally, we get the wave equation, which is c square and del square y over del x square and del square y and del t square. From that equation, we derive speed equation, which is c naught equal to square root of t naught and our density. So c is the speed of the low amplitude and transverse wave in a elongated form. So before that, shown the wave equation. So the wave equation is the mathematical formula that describes the long range free oscillation, and this equation is a second order linear independent differential equation. And this equation is proceeding according to the wave equation. We indicate this partial derivative equation is a hyperbolic. Okay, next, D'Alembert solution. A classical analysis of wave equation that's provide the D'Alembert solution. And the classical character of this solution is comes from the simplicity of this analysis, as well as the ability to give an idea of the phenomena of wave propagation. And consider the wave equation. Below, I've shown the wave equation, and use the result obtained from the wave equations independent to cone-shaped differential equations as are highlighted as a box shape. C square del square y and del square square and del square w over del t square equal to 0. From that, we derive comparing with we have the constant values and differential equation for setting the equation, and we have obtained these equations. Then the substitution equation in the wave equation we obtain from the conical form, we getting the del square w, our del and del n equal to 0. Then it will get to give w xt equal to f function and g functions. In terms of the x, the t variables we have is w xt equal to f x minus c naught t plus g bracket x plus c naught t. So this solution of D'Alembert solution can be interpreted as follows: if x mean the solution and w xt equal to f x minus c naught t at the time t equal to 0, when wx equal to fx, and this means the solution of fwxt equal to fx minus c naught t reflects a wave profile, and wx equal to fx is moving positive x direction in the constant c naught speed without the distortion. And similarly, fxt equal to g bracket x plus c naught t represent the wave of which moves in negative x direction with the speed of c naught with the distortion. And this is a diagram that physically shown what the equation says. which is in a moving wave. Okay, now I'm going to explain the solution of the wave equation by separation of variables. So let an elastic string be tightly stretched between the 2 points 0 and a. So the wave equation, just now earlier I shown, and c square equal to del square y w, and del x square equal to del square w over del t square, which is fxt equal to x function and t function. Let u equal to xt. So we substitute two equations with the different equations because x equation and t equations. Then we separate by separating variables. We get these three equations. So from that, we're getting the now auxiliary equation for above two ordinary differential equation, which is m square equal to kc square equal to 0, and m square equal to minus k equal to 0, and m equal to plus minus c square root k, and m equal to plus minus square root k. Hence, we have the three cases different values of k. The case one, when k is more than 0, then the auxiliary equations also already has two distinct real roots, which is c square root k and minus c square root k. And these solutions of the ODE is t equal to c1 exponential of power c square root of kt plus c2 exponential power of negative c square root of kt. Similarly, if a k is more than 0, the auxiliary equation of the ODE has distinct real roots, which is plus square root of k and minus square root of k. Thus, the solution of ODE is x c3 exponential power of kx plus c4 exponential power of negative kx. And case 2 is when the k is more than 0, the auxiliary equation of the ODE has conjugated complex roots, which is plus c square root of k. Thus, the order solution of ODE is t equal to c5 cos k square root of kt and c6 sine c square root of kt. Similarly, if k is more than 0, then the solution of ODE is x c7 cos square root of kx plus c8 sine square root of kx. Case 3, if a k is equal to 0, then the solution of ODE is t c9 t plus c10 and x is c11x plus c12. Since we are dealing with the wave equation, and suitable solution is case 2 when k is less than 0, hence the solution of the wave equation is wc7 kx plus c8 sine square root of kx times c5 cos square root of kt plus c6 sine c square root of kt. And the solution of the wave equation as wxt equal to c1 cos px plus c2 sine px times with the c3 cos pt plus c4 sine pt. So that is a solution by the wave equation by separation of variables. And thank you very much. That's all from me.
So now, thank you, Hilam. Now I'll be presenting on examples. So as you know, what is wave? Wave is a propagation of disturbance is what we call a wave. So now I have made my own graph to make it more easier. This is what I have drawn here. So we call the entire string is oscillating. We assume as the entire string is oscillating. So here at the x, it makes an angle of theta once it starts to oscillate, and x plus dx, it makes an angle of theta plus d theta. And the mass of the string is uniformly distributed. That means the density also is uniformly distributed around the string. Uniform tension in the string. So as you can see, I've labeled here T, another T. That means every point, the tension is same. And as you know, once the string oscillates, it only works on a vertical component, not in a horizontal. And the length of the segment, we call it as ds. So moving on. So the expression for ds is ds squared equals to dx squared plus dy squared. And once we convert it to the following reaction, we're going to get ds equals to 1 plus dy over dx squared powered by 1 over 2 dx. And as you know, I've drawn here the horizontal and the vertical component. So this is the equation, which is approximate to the 0. And the vertical component is I've listed here. And we have to convert this equation by using the PDE in the form of d, which is the tension, d square y over dx square dx. We equate the previous equation with the density times with the dx, d square y over dt square, which equals to the tension, d square y and over dx square dx. We convert this in the form of the partial differentiation form, and we're going to get d square y, and we have written here the dependence over dx dt square equals to t over p, which is the tension over the rho, d square y and the dependence x and t over dx square. So as you know, c square is equals to t over rho, which is the velocity of the wave. So we have to bring this t over rho equation to the left hand side. So once we brought them, the equation changes to 1 over c square over d square y over dt square is equals to d square y over dx square. From here, we are able to get the derivation of the one-dimensional wave equation. So this is how we're going to solve the 1D wave equation for the derivation. And I would like to pass to Adi for the conclusion.
Thank you very much. So most importantly, now we know that the wave equation has many solutions, and to turn it into a well-posed mathematical problem, you need to add boundary and initial conditions. So the equation can be treated as a pair of ODEs when you tend to use these variables. Unfortunately, because it depends on having two families of characteristics, this derivative only works for the wave equation and therefore wouldn't be possible for other equations like the heat equation or Laplace. When analyzing the initial data, we come to form a connection between the values of the solution and our initial data use. This showed us that the travel speed of the initial values was constrained by the wave speed, and the breakouts of the initial data travel along the characteristic lines. Thank you guys for listening to us, and hope we didn't take much of your time.